Hi learner, welcome on board this session. The topic of this session is drag polar. This topic is entitled to the subject flight mechanics. The target audience for this session are GATE aerospace aspirants, aerospace and aeronautical engineering students. We are following the flight mechanics syllabus for GATE aerospace engineering, and in this particular session we will be seeing about the topic drag polar under the subtopic airplane performance. In the previous lecture, we did know about the primary flight instruments, the link to which will be provided in the right top corner, and let's get an outline of this session. At first, we will be knowing about the drag, the definition of it, and the categories of drag. Further, we will be proceeding into the core portion of this session, that is the drag polar, and we will be knowing about the equation and the graph associated with the drag polar, and we will be getting about few insights regarding the drag polar. And further, we will be deriving the drag polar equation, and in particular, we will be also knowing about the induced drag coefficient. Let's get started. So drag. What is drag? Before getting about to know about the drag polar, we need to know or we need to have a clear understanding regarding the drag. So what is drag? So drag is an aerodynamic force that opposes an aircraft's motion through air. So here we can see a literally Airbus A380 aircraft owned by Qatar Airlines. So let's consider this aircraft is flying at some particular altitude. We have a velocity v infinity, that is a free stream velocity, acting on an aircraft. Now, what will be the forces of an aircraft? So let us consider this as an aerodynamic center approximately. So here we have four forces, or basically we will consider four forces acting on it. The first force will be thrust. So thrust is basically provided by the engine. So it is typically shifted, translated from the horizontal axis on in a vertical axis. So here we have thrust. It is one force, and the force which opposes the thrust is a drag. So here we have a drag which acts in the opposite direction to the thrust, and next we will be having weight, that is the whole aircraft has some mass, and this mass acts at a particular point, and gravity attracts this mass from a particular point known as a center of gravity. So here we have the weight, and to counter this effect of weight, we have lift, which is generated by the wing. So lift here is perpendicular to the free stream velocity. The line for lift may be slightly tilted. Still, when we talk about drag, there are only two general types of drag. We may have noticed that there are multiple types of drag. So all those types has to be some category based on these two general classifications. So if it is drag, it has to be either a pressure drag or a friction drag. So pressure drag is nothing but the drag which is caused due to the net imbalance of surface pressure acting in the drag direction. So any surface pressure, that is such as lift and other kind of forces acting in the drag direction, accounts for pressure drag. Friction drag is nothing but the drag caused due to the net effect of shear stress acting in the drag direction. So here when air flows closer to the skin of an aircraft, so fuselage or wing or any kind of surface, we can see that this action causes some kind of stress. So this stress is known as shear stress, and the drag caused due to this kind of stress is called as friction drag. From a basic perspective, you can remember this as a friction drag caused due to friction. So when we deal with drags, so there are basic terminologies which need to be known. So we will be coming up across these in this session and in the further portion of flight mechanics. So we need to know what those are. So here we get into the categories of drag, particularly in talking about subsonic drag definitions. So we will be coming around these terms, and we need to know what these terms really mean. So when it states as screen friction drag, it is nothing but the frictional shear stress integrated over the surface. So when we integrate the shear stress over the whole surface or skin of an aircraft, this provides us with the skin friction drag. So form drag is nothing but the pressure drag which is caused due to the flow separation. So particularly when we have an aircraft or any body moving around, there is pressure created around it, or the flow gets separated, or wake or similar kind of actions are performed. So this kind of activities provide us with the form drag. When we combine these both, that is a skin friction drag and the form drag, for a 2D case, that is for an infinite wing or an airfoil, this provides us with the profile drag. So profile drag is nothing but the summation of skin friction drag and form drag. Profile drag is also known as section drag. From section drag itself, we can understand that this is a 2D drag. So when we convert this 2D drag in for the case of 3D, that is when we consider the summation of skin friction drag and form drag for the whole aircraft, that is a complete airplane configuration, we will be obtaining the parasite drag. So this parasite drag, this term will be used time and again in this session and in the further portion of the syllabus. Now we will get to know about the next part of drag. So this is the interference drag. So interference drag is the basic difference between the total drag and the drag which is caused due to the individual component of an airplane. So if we know or get to know about the drags of each individual component of an airplane, such as the drag caused due to wing, the drag due to fuselage, the drag due to engine, and such kinds of drag quantities, when we add all those, it has to be equal to total drag, but it isn't, because there are other factors too. So for finding out this actual factor, we will be obtaining the difference between the total drag and the summation of all the drags caused by individual components. When we subtract this quantity from the total drag, we will obtain the interference drag. So this is basically caused due to the interference of the individual components with the air around it. The next drag, which is also an important drag, is the induced drag. Induced, as the term suggests, it is caused due to some kind of force inducement. So here, induced drag is a pressure drag which is caused due to induced flow. So the flow is induced. This induced flow is also known as downwash. So this downwash is associated with the vortices created at the tips of an finite wing. So when we consider the case of an rectangular wing, so let me draw a rectangular wing over here. So here, let me consider this is my wing. We know that there is high pressure on the lower surface of the wing, and there is low pressure on the upper surface of the wing. So basically, as per the laws of nature, the pressure tends to neutralize. That is, this high pressure air tends to get to the upper surface of the wing. This movement causes vortices at the wingtips. So this vortices causes downwash, that is, this is the induced flow, and the drag due to this is induced drag. And the next term is the zero lift drag. So the zero lift drag is a parasite drag which is obtained at the zero lift angle of attack. So the angle of attack at which the lift is zero is known as zero lift angle of attack, and we need to know that it is different for the cases of cambered wing and symmetric wing, which we'll be seeing about in the further portion of this syllabus. So next we will be seeing about the drag due to lift. So here we have the drag due to not cause which is not due to lift, and next we will be seeing about the drag caused due to lift. So this is the drag which is obtained at any other angle which is causing or producing lift. So this is the drag which is caused or obtained when we fly at some non-zero angle of attack, non-zero lift angle of attack. So here the drag due to lift is a combination of this drag produced due to lift plus the induced drag which is associated with the vortices. For better explanation, I prefer that you refer this portion of this book, Aircraft Performance and Design by J.D. Anderson, and the particular page numbers Page number 113 and 114 discusses these in detail. Now let's get into the core portion of this session. So drag polar, we did know about the drag. So what is drag polar? So drag polar is nothing but the equation and graph expressing the relationship between CD and CL. So drag polar basically provides us with the relation between the coefficient of lift and coefficient of drag. So let's get to know about this in detail. And before knowing it, we need to know what is the purpose of this drag polar. So drag polar provides us with the aerodynamic information which is indeed necessary for performance analysis of an airplane. So if we know the drag polar equation and plot, so this graph is basically plotted from the equation. So if we know this equation, this provides us with some aerodynamic information. This aerodynamic information in particular will be discussed in the further portion. So if we know this, we can analyze the performance of an aircraft. Now, talking about drag, when we consider the total drag of an aircraft, it is a summation of the parasite drag, the wave drag, and induced drag. So, wave drag is the term introduced over here. So, wave drag is nothing but the drag associated with the supersonic flight of an aircraft, and it is caused due to the shock waves. Now, let us write this equation, that is the typical literary equation, into the coefficient form. So when we consider this as in the coefficient form, so the coefficient of drag is CD. So CD, the coefficient of parasite drag is termed over here CD, comma E, and the coefficient of wave drag is CD, comma W, and the induced drag, the formula for induced drag is substituted, that is the CL square by pi EAR. So this formula is basically discussed in general in the first portion of the syllabus, and this is basically derived from the theory of incompressible flow. We'll be seeing about the it in aerodynamics, hopefully. So when we reduce this equation or further operate on this equation, we obtain an equation that is CD is equal to CD naught plus KCL square. So how did this we arrive at this equation? It is basically derived from this portion. So here we can see that CD is equal to CD naught plus KCL square. This particular equation is known as the drag polar equation. So we will be deriving this in the further portion of the syllabus. And before that, we will be discussing what is this equation. CD is nothing but the total drag coefficient, same as it is. So CD naught is the zero lift parasitic drag coefficient, and KCL square. So KCL square is here. So KCL square is nothing but the drag due to lift. So this portion deals with the drag which is caused due to lift, and this portion deals with the drag which is caused due to non-lift, or which is caused not due to lift. So as I said, there are two kinds of wing. So cambered wing or cambered airfoil, and a symmetric airfoil. So here we can see that the difference, basic difference. So cambered airfoil and symmetric airfoil. So here we can see the geometric difference between the cambered airfoil and the symmetric airfoil. And in particular, I would like to mention that in the cambered airfoil and the symmetric airfoil, the zero lift angle of attack differs. That is the angle of attack. So this alpha is the indication of angle of attack, and the angle of attack at which the lift is zero is different for both the symmetric case and the cambered case. So for symmetric case, we can see the zero lift angle of attack matches at the origin, that is 0. But for the cambered case, the zero lift angle of attack is some negative value of angle of attack, and we see that at 0 there is some kind of lift. So this is the difference. And as both of these are different, the drag polar equation also varies for the cambered wing and the symmetric wing. So this is a drag polar equation for cambered wing, and this is a drag polar equation for symmetric wing. The basic difference is that we introduce the CL minus CL minimum drag value. So here at zero angle of attack, we see that some kind of lift is generated. So this accounts for the CL minimum drag value. And when we replace the CL term with the CL minus CL minimum drag value, we can obtain the equation for cambered wing. In most of the cases, this is zero for literature purpose, but in actual case, it is in zero. Now we are getting to the second portion of the drag polar. So this is a graph. So based on this equation, if I plot the value of this equation, if I know the value of CD naught and the value of CL and CL minimum drag, K is a constant value. I can plot this particular equation, and it will provide me a graph similar to this. And similarly, if I plot this case of Dracula equation for symmetric wing, I will be obtaining an graph or plot like this. So here we can see the basic difference. So the for the case of symmetric wing, we can see that the uh, curve is starting from some particular point, and it is basically coming out from that point. But in case of cambered wing, there is a slight bulge, so the curve isn't like this. Instead, the curve is something like this. So here we can see the additional bulge, which is the basic difference for cambered and symmetric wing. So and we also need to see that the physical significance of it. When we plot some particular value of this Dracula equation, the first portion, so indicated over here, the first region, this whole region, um basically has a value of CD naught. So this is a value for one, and the second portion over here is the value for KCL square. So when we combine the drag for zero lift, that is drag not caused due to lift, and when we combine the drag which is caused due to lift, that is KCL square, we obtain the plot over here. So this basic region, so over here within this curve, provides us the equation or the graph for the drag polar. Now we will get some insights about this drag polar. Drag polar is nothing but the resultant aerodynamic forces plotted in polar coordinates, hence the name drag polar. We are tossing the term drag polar time and again. So what is basically drag polar and why is it called so? So drag is basically some kind of force. So when we plot that kind of force in polar coordinates, we obtain drag polar. It is mentioned in the definition. But for better understanding, let's consider a real case example. Consider a flight is flying at some particular angle of attack. So alpha over here is the angle of attack, and b infinity is the free stream velocity. So when the flight is introduced to the free stream velocity, we can obtain some lift, or basically there is two forces. Let's neglect thrust and weight. So it basically exists, but we are neglecting for this purpose. So there is a lift and drag, which is the lift is perpendicular to the free stream velocity, and drag is parallel to the free stream velocity. So due to the effect of lift and drag, there is a resultant force acting on an aircraft. So for due to lift, the aircraft gets lifted up. Due to drag, the aircraft gets pushed backwards. So both these actions need to be converted into a single force. So aircraft will be moving something like this. That is, drag pulls the aircraft backwards, and the lift pushes it upwards. So here, this particular resultant force is traced over here based on the lift and drag. And this resultant force will be acting at some particular angle theta, which is also based on the drag and lift. So when we plot this particular resultant force and the respective angle, we can obtain the drag polar plot, and this is respective to each angle of attack. So for this angle of attack, I am obtaining some resultant force value. So consider this false value as 1.1. Now I change the angle of attack, and the angle of attack is considered that it is increased. So for that case, the resultant force will vary, and it will be somewhat over here. So for that case, I will plot the another value r comma theta. So this will provide me with the second point, and similarly I will further vary the angle of attack, and then I will obtain another resultant force value r comma theta. So this is the third point. So basically these 3 points, when we connect these 3 points from the origin or some particular point, here we can see the cd naught value. If we know the cd naught value, we will start connecting these points, and when we connect these points, it is known as the locus. And when we connect all these points, which are based on the angle of attacks, we will obtain the curve for drag polar. So here we can see the procedure for obtaining the drag polar. And another point is that as I discussed, this drag polar provides us with some aerodynamic information. What are those aerodynamic information? So here we can see that drag polar provides us with the lift to drag ratio. So when I draw a tangent line from origin to the curve, so the tangent line from the origin to the curve, the first point joining the first point provides us with the lift to drag ratio. And when we draw the tangent line to the point of maximum lift to drag ratio, that is from origin to the second point, so we can see that second point is the highest point of the curve. So when I draw the a tangent line to this curve, it provides us with the maximum lift to drag ratio. So lift to drag ratio basically provides the aerodynamic efficiency of an aircraft. That is, we need to have a maximum value of it in order to achieve an efficient flight. That is, the drag has to be minimum and the lift has to be maximum. That is a design objective of a designer designing an aircraft. So it also provides us with the LD max, L by D max, or a maximum lift to drag ratio. And when I talk about this, so this point also provides us with the design point of an airplane or design lift coefficient for the airplane. So when I obtain the maximum L by D value or the maximum lift to drag ratio, this particular point, the corresponding CL value, that is somewhere over here, provides us with the design lift coefficient. So if the aircraft is flown over in this particular value of CL, the efficiency would be maximum. So this is how the drag polar equation and plot provides us with the aerodynamic information, which is used indeed for analyzing the performance of an aircraft. Now let's get to derive this equation, drag polar equation. As I said, we did obtain the drag polar equation as CD is equal to CD naught plus KCL square. So how did we arrive it? Let's start with from the starting case. That is, the total drag of an aircraft is nothing but the combination of parasitic drag plus wave drag plus induced drag. Now, when we write this in coefficient form, total drag can be written as CD. Similarly, other things, parasite drag as CD comma E, wave drag as CD comma W, and induced drag, the formula for the induced drag can be substituted from the theory of incompressible flow as CL square by pi EAR. So now in this case, let's get to solve these individually. Now first we see that the total drag is as it is, so we need to find this. Parasitic drag can be derived as a combination of the zero lift drag, that is drag which is not caused due to lift, and the drag caused due to lift. So basically, it will be having the drag not caused to due to lift as a CD, comma E, which is for parasitic drag, comma 0. That is, this is not influenced by lift. And next we will be having the drag which is influenced by lift. So here we can see the delta sign, that is a changing parasitic drag. When we further simplify it, we can write it as CD E comma 0 plus KCL square. KCL square is nothing but the value of the change in drag due to lift. Similarly, wave drag. Wave drag, as I said, is associated with supersonic flow and shock waves. In the similar manner, we can write the coefficient of wave drag as CD comma W comma not, which means the drag which is not caused due to lift, and K2 Cl square, which is the value for drag which is induced by lift, which are all also known as caused by lift. And the third portion of this equation is induced drag, and the induced drag can be simply written as KCl square, which is the value for the drag which is caused due to lift. And in all these terms, we need to note that the K is nothing but the inverse of pi E AR. AR is the aspect ratio, E is the Oswald efficiency factor, so pi is basically the value 3.14. Now, we have exuberantly discussed about this induced drag, and we have conventionally or comfortably replaced this value of lift induced drag with KCl square. So how did we obtain it? This is one particular point of interest. So when we get to derive this induced drag coefficient, that is CDI, we can see, let us consider case of a wing placed in an free stream velocity v infinity. So due to the effect of vortices, that is a wing temp vortices, as I said, consider this as wing, the high pressure flow and the low pressure flow. So when it tries to get neutralized, the high pressure flow flows from lower surface to the upper surface. So this similarly this causes vortices at the wingtips, and this causes some change in the inflow velocity v infinity. So here there is some change, that is consider this is at some particular angle of attack, and due to this induced flow the angle of attack is tilted to some particular small angle. So the free stream velocity is changed to v local, that is which is induced by the small change in induced angle of attack alpha I. Similarly, the lift force also changes, so there is a small change in the drag force due to the induced flow. So here we can see this is the drag flow in this particular direction, and it is shifted due to the induced flow. So what is the value of this induced drag? So induced drag, when we consider this as this angle is equal to the same angle, that is this angle is tilted by the same induced angle of attack. So this can be written as L. So here we can see that it is in vertical axis. So for this case, we can write the induced drag as lift L sine, as it is in this particular direction, and the angle is alpha I. So when we resolve this force, induced drag can be written as a product of lift and sine alpha I. So here we can see that it is obtained from the basic formula, that is sine theta is nothing but opposite by uh, hypotenuse. It is basically obtained from that basic equation. We will be getting to know about in the further portion of these lectures. So here now for this case, let us consider the induced drag is L sine alpha I. So as I said, the alpha I or induced angle of attack is very small, so we can replace the sine alpha I with alpha I, as there is no major change. And when we convert these terms in case of coefficients, or in terms of coefficients, we can write the di or induced drag as CDI, and the lift can be replaced with the coefficient of lift term. So here another equation is introduced, that is we don't know the value of alpha I. Basically alpha I is the induced drag angle of attack, which is obtained from the theory of incompressible flow. So this is a kind of two-page derivation. So we will be getting to know about it in thin airfoil theories, and when we know about these theories in the aerodynamic part of these lectures. So for now, let us consider alpha I, which is a derived quantity, as Cl by pi EAR. When we substitute the value of alpha I in the CDI equation, we can see Cl times Cl by pi EAR, and when we multiply the numerator terms, we will obtain CDI is equal to, that is the induced drag coefficient, is equal to the square of lift coefficient and divided by the value pi EAR. So pi EAR, the terms E is the Oswald efficiency factor, AR is the aspect ratio of the wing. Aspect ratio is nothing but AR is the square of the span of a wing by area of it. So basically, if we consider a wing, so this the length from the tip, one tip to the other tip is span B, and area, as we know, is a product of the chord and the span. Okay, we have obtained the value of CDI. So this is a basic part which has been introduced into each part of the equation. Now we can see that we did know how we obtained the coefficient of induced drag term, which has been literally used in every equation, that is KCL square. So here we will simplify the 1 by pi AR term as we will consider it as a coefficient. So proportionality coefficient, and we can write it as KCL squared. So this term has been introduced in every equation, so it is important. Now we have obtained the equations for individual case, that is we know the value for a coefficient of parasitic drag, the coefficient of wave drag, and coefficient of induced drag. When we substitute all these equations in the previous case, that is in the coefficient form equation, that is in equation 1, we'll be obtaining equation similar to this, that is CD comma E naught plus CD comma W naught plus the k terms are summed together, so k1 plus k2 plus k3 times the coefficient of left square. So when we basically group these non-lift uh, drag coefficient, that is a drag caused, not caused due to lift or not influenced by lift, as CD naught, and the k terms, proportionality coefficient terms, are also summed together as k, we can achieve an equation which is known as a Dracula equation. So finally we achieve that CD is equal to CD naught plus KCL square. The basic understanding which we need to have from this equation is that the coefficient of lift has two major contributions, that is drag or when we know about the drag coefficient, so it has two major contributions. So the drag which is not influenced by lift, and the drag which is totally influenced by lift. So these are both these terms. So here this portion 1 is the drag which is not influenced by lift, and here we can see the second portion which is the drag or drag coefficient which is influenced by lift. And for convenience, we in aeronautics used the coefficient terms instead of the force terms. Here we can see it is not plotted for lift and drag. Instead, it is plotted for coefficient of lift and coefficient of drag, as they are the non-dimensional values. And further, when we get closer into this portion or any portion, we see that there are multiple formulas which haven't been mentioned but is clearly discussed in books. So, discussing all these equations is beyond the scope of this session. Still, we need to know these equations in order to answer questions in GATE Aerospace Engineering. So, let me provide you a sample. So, here we have a sample. How do we calculate the CD naught value? So, let us consider the drag at zero lift, or which is not influenced by lift, can be written as Q infinity, which is nothing but the term for half rho v squared, which is also known as dynamic pressure. So this is basics, and the product of area and coefficient of skin friction. So this is nothing but the skin friction coefficient. CF is the skin friction coefficient. So here we can see that skin friction, we know the value of d naught. So from this, when we try to derive the further portion, here we also need to know about the S wet. S wet is nothing but the wetted area. So wetted area of an aircraft is the portion of the aircraft which interacts with the air. So basically, any surface or area which is being introduced to air comes under the wetted area. It is different from the normal area. So S over here is the planform area. So we know that drag coefficient is ratio of the drag. So CD naught over here. So CD naught is equal to D naught by QS. So ratio of drag by the other forces. So we are taking these forces to the denominator. So when we do that, we can see that we will obtain the CD naught value. So here in particular, when we consider the screen friction case, we know the value of D naught. When we substitute this value over here, we can see that Q infinity, that is the dynamic pressure terms, gets cancelled out. We will be remaining with the values S wet, that is a wetted area, by the platform area S times the CFE, which is the skin friction coefficient. So basically, in GATE exam, we will be provided with the plot or a particular value of this ratio and the screen friction coefficient, and we need to obtain the CD value, that is a drag polar value. So CD naught, for that at first we need to obtain the CD naught, and further we will be provided with the K value, the CL square, and everything. So here is this is a tricky part we need to know, and these kind of small derivations and equations are filled up in the textbooks, and I totally recommend you to read these kinds of literature in order to get a better knowledge, in order to um, answer these questions in GATE examination. So here, for this particular topic, you can refer the aircraft performance and design by J.D. Anderson, the 2010 version, which may be available with your college library, or you may use other resources. So here, the chapter 2 in particular discusses about the aerodynamics of the airplane and the drag polar. So it is concerned with the drag polar, and the particular page numbers which you can refer are 51 to 144 of it. And that's it for this session. We did know about the drag and drag polar. We had some insights regarding it, and we also derived the drag polar equation. Thank you. Let's crack GATE Aerospace Engineering.